Okay, but something you can see. Maybe it's established. And these actually is a pleasure to have Suggest Murugan, not from city, also down the road. Until a few months ago, just the acting GBC research at UCT, but his main job as sort of physics, the mathematics and applied mathematics, and UCT. And also, the spreading of misinformation in social networks or yeah, thank you very much for you give us a talk. It's it will see very interesting topic.
Thank you, Francesco. Thank you for the invitation. Thank you very much. It's always a pleasure to be here at Stellenbosch. It is down the road, but it's I feel like I need a visa to come there. So thank you very much for the invitation. It's great to share a little bit of some of the stuff that we've been thinking about. How this arose, as Francesco mentioned, I'm a mathematical physicist, and I usually spend my time thinking about quantum many-body systems. If this helps, this is a classical many-body system. As Francesco pointed out, until this year, I was the acting DVC for research at UCT, which means I get to be part of lots of WhatsApp groups, lots more WhatsApp groups than I'd like to be part of. And circa the middle of the year last year, we had an interesting experience where the COO informs the executive group about something that happens on campus at about 9 a.m. in the morning. At 7 a.m. in the afternoon, my wife gets a imagine quite alarmist. And I thought, this is crazy how this information has gotten morphed from 9 a.m. to 7 p.m. It sounds completely different. I wonder if we could model that. So that's the outcome of this. So to start, I want to ask a question. It's a kind of a rhetorical question, but I'm hoping this gets everybody thinking about the way we think about information. And this is the question of we seem to not be moving forward.
Swipe over and click on your slide.
Hey?
Swipe over with your mouse and just click on your slide.
Okay, so we'll go with that then. Right, so the question is, where do we get our information from these days? And for some of you, it will be radio. My children have no idea what I'm talking about when I say that. Some of you, it will be family chats, WhatsApp groups, TV. I barely understand that concept. Community alerts, or Twitter, or whatever it's called these days. And sometimes it's email notices. And for many of the younger generation today, it's TikTok. The key point here is that it's less and less newspapers. And this is important about the type of information we get and the way we filter the information that we get. I want to focus on specifically, because it's a much easier problem than dealing with the one that I really want to deal with, one particular platform in which we get our information, and that's WhatsApp groups. And there's a reason why I say that this is simpler than thinking about how we all convey information and interact with information as social animals. So we're going to focus just on WhatsApp groups, and I'm going to tell you about the model that we set up to model specifically the way information degrades as we get it, as we transmit it, as we interact with it. So I want to start because I think we've all kind of, ever since 2016 when fake news became a thing, I think we've all kind of engaged in some way or the other with the concept of misinformation, right? Information that is in some way or the other that we'll try and quantify, not particularly true, but has some semblance of truth allocated to it. I want to just say, to start off with, initially I'd set off trying to understand the concept of disinformation. And I want to disambiguate disinformation from misinformation. So disinformation is the deliberate spreading of low truth value information. I'm not talking about that. That's a much more difficult problem to think about, and it's something that we're currently working on at the moment. But I want to focus on misinformation. So the idea that some information starts off with what we're going to call a high truth value is something that is true, and I'll tell you how we'll think about that, and how that truth value diminishes as we move through the network or in time. So then we're left kind of asking the question, why does misinformation persist? Why does misinformation arise? How does it spread? And if you ask a general population about this, there are a number of guesses that we can make. One of which would be simply bad actors, people that have a particular agenda or not, and try to convince you of something. So these are people that inject deliberate low truth value information. Right? This is what I just explained is what I will term disinformation, and I'm not going to be talking about that. The other one is gullibility. We tend to believe things based on the things that we already believe. So this is the confirmation bias that you would have heard a lot about, during COVID times, where people believe something, and then if I tell you something, you evaluate that something based on your already existing belief structure. So a not so nice way of saying the same thing is people are gullible. And then there's the idea of polarization. Again, you tend to go into any particular situation with some particular belief that aligns with something, and then the way you interpret the information that comes out of that depends on your prior. Okay, so this is what we would call polarization. So all of these things, all of these guesses kind of lend you to believe that people aren't informed, that people aren't educated, that you could solve this problem by educating people and telling them more about the thing that you want them to believe in. For example, vaccines are good. And it turns out that it's not necessarily the case. It turns out that even careful, educated people spread distorted information. Sometimes intentionally, sometimes not intentionally. And it's this kind of dynamics of information that I'm interested in this talk. Right? And I'd like to convince you that, people are not inherently bad in spreading information. And it's the structure of the way we communicate through social networks, and particular through the WhatsApp type networks that we're all, that's kind of pervaded our lives, that even careful, educated people without any malintent can spread distorted information. Okay? So throughout the talk, there are these little yellow boxes, and I'd like you to pay attention to those because those are kind of the takeaway messages from this. Right? There's some math involved. I don't know what my audience is. It's not a lot of math, and I'll talk you through all of the math, and I'll interpret all of it for us as we go along. Okay, so the question is, how does information the president pigeonholing populations, right? So you take your population group and you split them into, let's say, three boxes at the moment. One box is susceptible information. They're susceptible individuals. These people haven't heard the information that you're trying to propagate, right? So they haven't been, they haven't interacted with the virus. Then there's the people that have had exposure to the virus and that are infected. That's the infected population. And then there's some set of people that have recovered. So the general dynamics of these kind of SIR models, SIR standing for susceptible, infected, and recovered, looks like that. I'm not going to unpack these equations because they're not really what I'm interested in. The point here is that SIR models tell you who's infected, but it doesn't tell you anything about the information, right? So the question is, what about the content of the information? So these SIR models tells you who has the information, but it doesn't tell you anything about the quality of the information. And we know that information has quality. Information has nuance, it has details, and those details actually matter. One nice way of thinking about this is something we're all kind of familiar with, which is the photocopy effect, right? If you take a picture and you, the photocopy effect, right? So you take a picture and then you photocopy the picture, and then you photocopy the photocopy and you photocopy the photocopy of the photocopy, right? What happens is you get a degradation of that picture. It gets worse and worse every time you photocopy it. All right? So information doesn't just spread, it also degrades. It degrades over time and it degrades over space. And we're interested in the degradation of that information. So as an applied mathematician, my job is to try and understand what this means quantitatively in order to be able to make predictions and changes to the system should I want to. So I need to understand what I mean by the truth value of the information. I'm going to track it by what's called the fidelity of the information. And the fidelity of the information is essentially how close is what you know to the original message. Okay? And to account for nuance and details, I'm going to model fidelity as a continuous variable that ranges between 1, which is pristine information. I've just injected something that I know and I can verify as true, to 0, which is completely distorted information. Right? And I'm going to model it on a spectrum. So it's not going to be binary, yes, no. It's going to be somewhere between 0 and 1 in a continuous way. Right? It could be 0.32, be 0.001. So we're going to think of the fidelity or the truth value of the information as a continuous number that can take values between 0 and 1. Right? So in physics, we call this a field. It's going to be a scalar field for any physicists in the audience. And that's what we're going to be trying to understand. So it turns out that fidelity, even by itself, fades. Right? So if I hear something and I don't talk about it, I don't do anything with it, right? Does it stay pristine? And the answer is no. Well, it's because memory fades. We forget details, right? This we can model as something analogous to, say, radioactive decay or signal damping in engineering. And basically says that the change in the fidelity decays proportional to what the fidelity was. Right? This is a simple equation that first-year students would see, and it's easy enough to solve. It's a first-order differential equation, and it basically says that information decays, the fidelity decays exponentially. Okay, so will fade, and the information that you have will degrade by itself, and it will degrade exponentially. So that's the one effect. I'm going to take all these effects and I'm going to build them together and give you a dynamical system for how information flows in a system. The second point we need to take into account is nuance is fragile, right? complex messages degrade faster than simple ones, and that's because people forget details. If I give you a really detailed piece of information versus something that's really simple to remember, it's easier to remember the simple piece of information than it is to remember the highly nuanced information. So people tend to remember just broad brushstrokes, and they forget the details. Okay? So this is something that's already observed in classical Shannon information theory, and it's modeled as what's called Riccati decay. Right? So that is the statement that the change, this is what that dot means, the same as the d by dt in the previous slide, the change in the fidelity is not only proportional to the fidelity, but it's also proportional to the square of the fidelity. So for those of you that are in first year, second year, applied mathematics or mathematics, this kind of looks a little bit like what you would call logistic growth. Logistic growth is what happens if you take a competing population and you put it in a finite box. Eventually, they start off by growing like two rabbits in a pen. Right? They start off growing exponentially. The population grows exponentially, but eventually, it starts to hit the boundary of the system, and then it starts to be competitive, and then it'll slow down. Right? So you get this S-shaped curve that is typical of what we call logistic growth. This is almost like that, except that here the behavior speeds up rather than slows down. That's why this minus f squared term here. So for people that study dynamical systems in this audience, there are two fixed points in this equation. Fixed points are where this side is equal to 0. They happen at two places, either 0 or it's minus delta over beta here. This minus delta over beta, given that we're talking about the truth of a system and it ranges between 0 and 1, any negative number is not really physical, so we exclude that. This guy here is important though. And these arrows here tell me that I can think of this as like a river flowing. If I start off here, the arrow tells me where I will end up. So if I start off here with some positive value of the fidelity, the arrow tells me that I'll work my way to 0. If I start off here, I'll also work my way to 0. This is what's called a stable fixed point in dynamical systems. Essentially, what it's telling me is that the fidelity always decays. Right? And in fact, it decays faster than just memory effects by itself. So the story so far is that information is not binary. It's a spectrum. Fidelity decay is a measure of how information degrades, like that photocopy effect that we were talking about. And that complex information degrades faster. People tend to forget the details of what you tell them. They remember broad brushstrokes. Right? So now what I want to do is, so all of that was basically just information by itself. It's classical Shannon information theory. Right? Now what I want to do is I want to add social interactions, because that's what we're interested in. We're interested in what happens when you're in a social network on WhatsApp, for example, right? How does the structure of the social network impact, if at all, the story that we've developed so far? Social interactions are complicated, right? So you can think of each dot in this as an individual in some kind of social network. And it's complicated because people form parts of groups. Those groups change. You're a member of a group. One day you get kicked out because you're not in a union anymore. The next day you talk to somebody in a one-on-one chat, and then you're not friends anymore, so you don't talk to that person. All of that is coded in this graph. This is what mathematicians call a graph, and it has specific properties. So before telling you about what WhatsApp looks like, let's just talk about graphs. We'll talk about networks and their architecture. It's actually not that difficult to grasp. So here's a network, right? It consists of nodes. These are these dots. And the lines joining those nodes. So a line joins two nodes if two people are connected, right? So just keep in mind the WhatsApp network that we want to talk about. So each dot here represents a person. And each line represents a relationship between those two people. Okay, so this is what mathematicians call an edge. You have nodes and edges. You also have faces, but we're not going to be interested in the faces at the moment. So 3 nodes, for example, form a triangle, and that triangle you can color in this space here. That's a face. We're going to be interested in the nodes and the edges that join these nodes, and the various different types of structures that come out of that. So one type of structure is what mathematicians would call a loop. Okay, a loop is a closed path in this network. Right? And for our purposes, you can think of this as a WhatsApp group. Right? So people interact, and they interact in a group. Bunch of people connected in particular ways. I can join all of these together. It doesn't really matter. The point is that I form a group out of this. The other type of structure that's important is a hub. So this is one person who's connected to everybody. Okay, the more highly connected you are, the more of a hub you are. So those are the different aspects of the graph that we're going to be interested in for the purposes of this talk. So now I want to talk about different layers in a network. Okay, we're going to be interested in a WhatsApp-like network, which is an example of a multiplex network. And a multiplex is made up of different layers, and those different layers represent different things, and people in that layer interact differently with other people in that layer. And what makes a multiplex network complicated is the different layers interact with each other. So just by way of a short digression, this work, the kind of, the tools that we built on in this work came from a particular problem that I worked on with an honor student of mine in 2021, just post COVID. So basically, we were in the situation where South Africa had some vaccines, but we didn't have lots of vaccines. We had less vaccine than there were people in South Africa, unlike Canada, for example. And so the question became, if you've got a finite stock of vaccines, right, how do you distribute this to a population? What is the optimal strategy for vaccine distribution? And it's particularly relevant to South Africa because we have a particular population structure. If you take a very homogeneous society like Japan or one of the Nordic states, for example, the way this like South Africa. So in South Africa, we have people that live and within the metropole, people interact in a particular way. Within the suburb, in a particular way. And within the townships, people interact in a particular way. Now, if we could group all of these populations and see how they interact, the issue becomes the people in the townships interact with the people in the suburbs and the people in the metropoles. And so you have this layered structure where everybody's interacting with each other. That's the difficulty in modeling. So the mathematical methods that went into this came from that study applied to a different problem. So what we're going to be talking about is a network that looks something like this, right? It's a little bit more complicated looking. It's a 100-node network. So let's think about a WhatsApp group of about 100 individuals interacting. And you can see, connecting all the relationships between people makes it a complicated network. In and amongst these are exactly the same structures that we talked about. Loops, basically groups of people interacting within that group. And then individual interactions, one-on-one interactions that look like this. And then you'll see some of these lines, these edges have arrows on them. And the arrows indicate that they're part of a broadcast network. And in a broadcast network, information flows in one direction only. Somebody, I'm sure you're all part of a broadcast network, right? They don't let you reply to anything. So that's the point. Information flows in one direction, and that's denoted by these arrows. The arrows flow in one direction only. One-on-one chats are bidirectional, and group chats are multidirectional. Okay. So that's the system that we're looking at. That's a cartoon of the system that we're looking at. And now I want to start by asking a particular question. In the last couple of slides, we've learned that information decays. So information degrades, and we're modeling that by fidelity decay. So if fidelity always decays, how does any information survive at all? Okay, so I showed you that 0 was a stable fixed point, so the fidelity is going to decay to 0. 0 is going to be completely distorted information. So if information always decays, degrades, how does information survive at all? Okay. The answer is broadcast layers. Information truth injection into the problem. So broadcasts act as a source, not an exchange. You don't get to tell the broadcaster what you think is true or not. They inject information into the system. Okay? So listener changes. So if I think about the ith node, the ith dot, I'm just labeling the dots, right? If I think about the ith node in this network, okay, as having fidelity, holding some information with fidelity. Remember, fidelity is a continuous number between 0 and 1. So they hold information with some fidelity, call it Fi, right? When you hear a broadcast, the listener changes. So Fi changes. The broadcaster has some information. We'll call that information FB for broadcaster. And the point is that because the information is unidirectional, FB doesn't change. FB stays the same. If the listener matches the broadcast, in other words, if Fi and FB are the same thing, you hold the same information that's being broadcast to you, then nothing happens, nothing changes, nothing should change. Okay, you hold the same information, you're just hearing the same thing. You don't expect anything to change. You don't expect the information that you have, the fidelity of the information that you have to change with this. Does that make sense? Okay, so broadcasts on average, then they don't average opinions between the broadcaster and the listener, right? They pull you towards a reference. Okay, so broadcasts pull towards a reference. If the information that you hold is less than, if the fidelity of the information that you hold is less than the fidelity of the information of the broadcaster, then I expect that the fidelity that you hold will increase because you're getting a higher truth value information and you pull towards that reference point. Okay? If the fidelity of the information that you have is greater than the fidelity of the information of the broadcaster, I expect that your fidelity will decrease. Right? You're getting some injection of information. You're taking that as having better knowledge than you have, right? And so I would expect that your fidelity would decrease as a result. So we're going to assume what's called linear response, which is that a small mismatch will result in a small correction. Okay, so whatever happens, how the fidelity of the information you hold, that's this guy here, changes, that's what the dot means, should be proportional to the difference between the fidelity between the broadcast and what you already hold. That's what this equation means. This D3 here just tells you just how strongly you believe the broadcaster, Fox versus anything else. Okay. Okay, good. So that's how broadcasting works. How does a careful one-on-one conversation affect information fidelity? The key point here is careful and one-on-one, right? So these are individual to individual in the network, and I'm asking if this is a careful conversation, right? I'll tell you a little bit about how, towards the end, about how emotion influences these discussions. But for now, careful, logical conversation, one-on-one with somebody that you trust, say. How does this affect the information fidelity? Well, I expect, so I'm just giving you the principles, and then again, that's the takeaway. The principles here should be that interactions should reduce differences, not create differences. Okay? So they should increase the lower fidelity, they should decrease the higher fidelity, and they should reduce the difference between the two fidelities, between the two individuals. Okay? And the only kind of thing that I would expect to then matter is if individual J has fidelity Fj and individual I has fidelity Fi, then I expect that the change should be proportional to the difference between the two, Fj minus Fi. Further, I expect that the interaction should conserve the total information quality, right? So in a careful conversation, I expect that information is refined rather than created or destroyed. You hold some information, you hold some information. When you chat to each other, I expect that the interaction would refine the information that you have rather than create new information or destroy the information that you already have. So that's principle number 2. And then finally, I expect that multiple independent interactions should add. So you talk to you, you talk to you, you talk to you. I would expect that all of these things refine your information content further in an additive way. Right? Pretty simple assumption to make. So essentially what I'm saying is that the change in the fidelity of your information, observer I, this network, should be proportional to the sum of the differences between all your different interactions in a linear way, just straight up difference between Fj minus Fi. And you should add all those interactions that you have with everybody in the network. Okay? So this is a very particular case of something more general that graph theorists would write this way. So this quantity here is what's called the graph Laplacian. And all this is what's called diffusion in a network. So this works in any network. If I set up a lattice of electrons interacting with each other and I stick some energy into this thing and I wonder what happens to that energy, it'll diffuse through that network in exactly the same way. So this is really telling us about diffusion in this network. Right? And I want you to keep this in mind because the one thing that is clear about diffusion is that it is a slow process. Okay. Good. So now we understand broadcasts, we understand private chats. So the next question is, how does a group discussion work? And in particular, how is a group discussion different from a collection of private chats? So now imagine that, everybody in this room is talking to everybody one-on-one. Those are private chats, right? And they change your fidelity in some way, which we've discussed. But now you bring everybody together and you let everybody have an opinion in the same room. And I want to know what's the difference between that and a collection of private chats. And there's a marked difference. The overall takeaway from this is that group chats lead to groupthink in the following way. So groups compare information fidelity to a norm, something that is kind of the average of what people think, right? So the way to think about this is when you're in a group and you want to poll the group, you ask, what does the group think? When you're in a group and you think slightly different before you voice your opinion in a WhatsApp group chat, you kind of always ask yourself the question, what is the acceptable position to hold in this group? What's going to get me kicked out? What's going to get me part of the in crowd? All of this mathematically is comparing fidelity to a particular norm value that the group takes. So I have to define what I mean by the norm here, and I have to give some representation of what the norm is. And the simplest representation of a social norm is basically the mean, the average, right? So I take the fidelity of every member in the group, and I divide and I add them up, and then I divide by the size of the group. And that will give me the average, right? So that's basically what I'm defining. So this is the mean value of the fidelity in the whole group. I'm going to call it FG bar meaning the average, G meaning the group. Okay. Change of opinion, of fidelity in a group is driven by deviations from the norm. Right? And the driving force then, again, I'm just telling you the principles that I'm going to apply and then what that's going to mean for the equation, and then we're going to take the equation away and chuck it into the big system. So the driving force must vanish if your opinion is the same as the group's opinion. So if your opinion is the same as the group's opinion, you're not going to change your opinion. The only available linear structure that maintains this is the difference of your opinion from the norm. Right? The bigger the difference, the bigger a different fidelity information you have, the bigger difference of opinion you have from the group, the bigger I would expect the change in your opinion to be. Right. So that's the only information, the only available structure. So here, the change in your fidelity must be proportional to the difference between your fidelity and the group's fidelity. Okay? And again, how strongly you're influenced by that group is coded in this variable D2. Right. So there's an important point to take away from this. This is just some simple math. If I take if I calculate the change, that's what the dot means again, in the norm, right? The change in the norm is the change, if you look at my definition there, this G is a constant, it's just the size of the group, is the change of Fi summed over I, which is D2 over mod G, Fg bar minus the sum of the Fi's divided by G. In other words, Fg bar and Fg bar, and they cancel, exactly, 0. Right? And I said I'll unpack the math. Essentially what this is telling us is that groups don't improve information quality. They only enforce consensus. Right? That's what this piece of mathematics is telling us. Groups don't change information quality, they enforce the consensus of the group. Okay? And I haven't given any details. The only thing that's sitting in here is the structure of the network. Okay, so now I can pull together all of this information. In a WhatsApp-like network, the change in the fidelity of the ith participant in that network consists of a couple of things. There's the fact that there are these two intrinsic terms that depend on the individual themselves, particular that individuals forget things and individuals forget complex things faster. That's what these two terms tell us. And then all of this is the social network. They depend on the network, they're topology dependent, and they reside in 3 communication channels: group chats, individual chats, and broadcasts. And that's all coded into this. So this is the dynamical system that governs the fidelity of the information. Okay? So now we can solve it. It's a differential equation that we have to solve. But before we do that, I want to unpack one more thing, which is social butterflies. Right? There are some people that belong to more groups than just one. Right? In the network, this is kind of what we're looking at. So here, this individual here belongs to this group. They also belong to this group, and they also belong to this group. So they're what we call bridge nodes. They bridge different groups. And these bridge nodes actually turn out to be information bottlenecks in the following way. So the key point here is that a bridge node is pulled in many different directions. So remember, if you're part of a group, the group's trying to get you to conform to the group, what the group thinks. And if you're a bridge node, then you're being pulled in any one of many directions, each trying to convince you about something. Okay? So imagine being part of a parent network and an academic network and a union network, right? And some piece of information comes about. Each group believes different things, and each group's trying to get you to believe different things. You have some information, it's already fading, but in addition, it's being shaped by the interactions with the different groups. So a bridge node is one that's pulled in many directions at once while simultaneously losing information. So essentially what we're saying here is that the change in the fidelity held by the bridge node, by the individual that belongs to multiple groups, depends on some things that are just cognitive overload, just you're forgetting things, right? And then it also depends on how you interact in the various groups. So this is a sum over the different groups that you belong to. This number here tells you how strongly each group enforces conformity to that group, to the way that group thinks. And this tells you how far out of line you are with group J. Okay, so some groups, you totally believe what they say. You're close to the group norm there. Some groups, you're far away. Okay, and this is coding how that works in each of the groups, and then I'm adding all of the contributions from each of the groups. The point is that I can solve this equation. I can solve it for what's called a steady state, and a steady state is where nothing's happening. It's steady state. Okay, so there's no change, which means that this is 0. So then I can solve this equation by setting it equal to 0, and I get a steady state solution which looks like this. Point of this is that social butterflies are the weakest links. People that belong to multiple different groups have a big impact on the information transfer across those groups. They don't just transfer information, again, information from different groups. And that's what that steady state is telling us. So basically, and this is what I said about not being malign and smart, intelligent, educated people also spread misinformation. This is how they spread information. It's not behavior. It's the algebra of the equation that we're talking about. Fidelity drops. Just going back. Fidelity drops with more groups. The more groups you behave in, the bigger the denominator is. The bigger the denominator is, the smaller the ratio is. So fidelity drops with the number of groups as well as the group size. Okay? And then you have intergroup contamination where one low fidelity group actually affects many other groups if they have bridges joining them. And we didn't even require malice. We just required to be part of the group and the group dynamic being averaging to the norm of the group. Okay? So that's the takeaway from this. Bridge nodes don't just transfer misinformation, they actually manufacture it by mixing the norm of different groups. So here's the story so far. If I inject high fidelity information, so fidelity equals 1 information, and so this is a numerical solution of the differential equation. If I inject high fidelity information into this, what happens is that into a WhatsApp-like network, you get rapid decrease of the fidelity of the information to less than half, right? Over a very short time scale. Then broadcast reinforcement happens, and that turns the behavior around, so it corrects a little bit for it. And then very slowly, you get this kind of logarithmic tail of one-on-one corrections kicking in. But you never actually recover the fidelity of the information. It always lands up being slightly over half or so. Right? So the question that we have to, so this is the story that we've come up with just now. And there's an important lesson to be learned here as well. Firstly, there are 3 timescales involved. There's this, I don't know if you can see it from the back, but there's this darkish orange, slightly lighter-ish orange, and then this kind of beige color grouping here. They indicate 3 different timescales. The fastest one of which is the rapid drop of fidelity when you inject information into a group. Then you get this corrective timescale that comes from broadcast. Then you get this corrective timescale that comes from careful one-on-one chats. Okay? Okay. So the question to ask is, what does the system settle down to? What is that final value that it kind of settles down to, and what does it depend on? So here, there's a kind of a conservation law for fidelity of information. If you average out over the network and over time, so that's what these angular brackets mean here, and F here is the, F with these funny brackets around, with the angle brackets around, means the average F, right? You get an equation that looks like this. I don't really care too much about what the equation is itself. What I care about is it's an algebraic equation. There's no differentiation involved. There's no calculus involved. It's just an algebraic equation. I can solve it for F. And when I solve it for F, I get the following structure. It's actually quite a simple structure that indicates that the average value that it settles down to over that long time period is determined by 2 things. One is the numerator and the other one is the denominator. The numerator here is injections of truth that come from broadcasting, right? Remember this factor D3 and the PB here are broadcast level variables. And then everything in the denominator is everything that fights against accuracy, right? So this is important if I want to determine what the long time fidelity is in a system. So if I want to kind of think about how do I change the structure of the network? Is there something about WhatsApp that I can do to change its structure in such a way that it influences the long time fidelity of the information that goes into any WhatsApp network? I haven't specified who's in the network. I haven't told you anything about the network other than its actual architecture. right? So this is a very broad general statement. Injection of truth in the numerator, everything that fights informational accuracy in the denominator. Okay. So now we can ask questions like, why is it that fact-checking always seems too late? You're part of a WhatsApp group, somebody says something, it sounds ridiculous, and then eventually somebody will fact-check that person and say, well, that's not the case. And I mean, if you go on Twitter and watch American politics right now, and you see what I mean. Fact-checking always seems like it comes too late. Why is that? Well, it has to do with the separation of scales that we identified in the previous slide with the graph on it, those different colored orange patches. So we can look at the system, we can look at all the equations that I've given you so far, and we can do some dimensional analysis. So dimensional analysis, for anybody who's not a mathematician in the room or physicist, is basically some algebra that you do to check that everything in an equation has the right units. So if I have something on the left-hand side of an equation and I have something on the right-hand side of the equation, they must have the right units. I can't compare length on one side to time on the other side, right? So I need to check each variable to see what the dimensions of that variable are. That's what we call dimensional analysis. Okay, so I can look at each of these equations and I can find time scales in those equations. And those time scales from those equations fall into three categories, right? First is group dynamics. That comes from the equation that we wrote down for how fidelity spreads in the group, right? There, the characteristic time scale involved goes like this 1 over md2, which is the strength of the group interaction, right? The point here is that group dynamics happen in parallel and they happen fast. Broadcast dynamics are uniform. One broadcaster spreads the same in fidelity to everybody in the group at the same rate. This is slightly slower. It goes like 1 over d3. That's a characteristic time scale of the broadcast. So in a broadcast network, that is the characteristic time scale that determines how fast information spreads as a result of a broadcast. Then I get private chats, this one-on-one chats. And remember I said that the equation that we wrote down for the one-on-one chat was basically diffusion. Well, diffusion is slow. So the characteristic timescale that that's involved in diffusion, the private chats, is the slowest of the lot. So if I have to organize these timescales, group timescale is much smaller than the characteristic timescale for group dynamics is much smaller than broadcast and much smaller than private. So the dynamics organizes itself in this particular way, that whatever's happening in the group is going to happen the fastest. Then comes broadcast after the group chat, after the group averaging. That's why fact-checking, which is a broadcast level activity, always seems like it's too slow. Stuff in the group has already happened, right? So essentially, misinformation wins because it is just faster. It spreads by this time scale. Okay. Which leads me to my final slide, which is why does this all matter? Well, unlike the other things I do in my job, this has real world implications. By the other things, I mean, I usually like study black holes and stuff. So this has real world implications. We've seen this happen, right? Election information, health misinformation, crisis communications. I'm from UCT, we have lots of crisis communications. All of these things are real world things, right? So understanding how misinformation spreads is tantamount to understanding how information spreads and misinformation spreads in these contexts. And we've all had and experienced these contexts, okay? One of the things that we've learned out of this is that individuals are not entirely to blame for the misinformation that spreads in WhatsApp groups. So even if people behave rationally, even if people are intelligent and want to communicate sensibly, it turns out that the platform architecture itself amplifies distortion, whether or not it intends to do so, right? This is just the mathematics of the network. It amplifies the distortion of the fidelity. And then finally, understanding how this works in this context can maybe help understand how to stop it happening. In particular, structural interventions can help, right? The goal here is that final time averaged fidelity that we were talking about, that tail end of that graph. We want that tail end of the graph to be higher, so that over a long time, the fidelity held by the group is closer to the truth than to fidelity 0, right? And having worked out what the average fidelity looks like, we can read off that smaller groups help, fewer bridges help, and wider broadcast reach, that D3 value helps. So this gives us kind of structural ways of changing the way the network looks to improve the long-time fidelity of the system. And I guess what I'm saying here is that essentially misinformation is a physics problem. And if it's a physics problem, then it's an engineering problem. And if it's an engineering problem, then it can be re-engineered. And that's what I have to end with. Thank you.
That's a very long question.
So you had a graph.
Yes.
And you also talked about the other kinds of graphs.
Yes.
But after you finished talking about the other types of graphs, it wasn't clear how the rest of the presentation relied on the structure of those graphs. Specifically, in this graph, does this graph apply to any structure or not?
No. So the structure of the graphs, let's call this a plot. Right? The structure of this plot depended on the structure of the graphs because of the topology of the graphs. So those determine the differential equations that govern how the information flow. I then took all of that and I put it into one differential equation, and then I solved that differential equation numerically, and this is what comes out of that.
But which parameters did you use for that specific solution?
Oh, I can't remember, but this was the shape of this graph is not particularly dependent on the parameters. Okay. It'll change, where the minimum is, it'll change the slope here, but the overall shape will remain the same.
Okay, thanks.
Yes, I have two questions. So the first one is, I think there's a very important aspect which might constitute the good next thing to add to the theory, which is that different persons have different strengths. So if like a professor chats with the student, probably the student is going to change their information much more, but probably not. Probably not. But the other example is like so maybe the sum of the derivatives is not always.
Right. Good. That's one.
Yeah.
You have two questions, right? Yes.
Could your theory be applied to model the mutation of the viruses?
Yes.
In
Yes. Okay. So again, this kind of my interest in viral spreading was the same as everybody else during COVID. Everybody thinks there was an expert at me too. So in 2020, with a student of mine, like early 2020, kind of February or so, right? So Donald Trump says, Donald Trump version 1 says, I've shut down flights from Wuhan to New York. Everything's going to be fine, right? And that sounded like, can I swear? That sounded like rubbish. So we wanted to demonstrate that it was rubbish, but I wanted to do it in a way that was convincing. So with the same student that I studied the vaccine dissemination problem, we thought, well, how could we do this? And we thought, essentially, we could put it on a graph, right? Where each node in that graph was an airport. And each line was an actual flight path between the two, right? So it turns out you can go online and you can scrape web information about different airports, and you can actually construct a proper model of this. So we did that. And if you say, well, I have this graph and I have node Wuhan and I have node New York, and I want to stop the spread of the virus, right? Without turning off all the interaction in the whole world, right? Then mathematically the statement is I want to take this node and I want to take that node, and by the metric that I use to measure distances on that network, so not physical distance, network distance, I want to take these two nodes and I want to move them infinitely far apart without disconnecting the whole network, right? So that's the mathematical statement. And there's a theorem, which my HOD, who is a graph theorist, told me about. There's a theorem that says that you can't erase a finite number of edges in a network and do that and take any 2 points infinitely far apart from each other. However, you can, if you find one of these highly connected hubs and turn that hub off, right? So there, the physical statement is just erasing any finite number of direct paths from Wuhan to New York is not going to accomplish this. However, if you identify a highly connected hub like Dubai, right, and turn that hub off, then you can. Okay, so that's a more efficient way of stopping the spread of the virus. So we wrote a paper about it, and nobody cared. And we realized that politicians are not going to read math papers. So what we did was we built a user interface where you could use these SIR models, the very simple models, and real time in the user interface, you could go and turn off this airport and see how it affects the curves. And that was cool, but nobody cared either. But by that stage, we were kind of all bored at home and moved on to other things. And I totally forgot what your question was.
The first one or the second one?
The second one, I think.
The second one is that, so you were saying there's this analogy with the epidemics, the virus.
Yes.
But
oh, yes. Your question is, can I take the stuff that we're doing with the information spreading and move it to that space?
Yes, to model the mutation of the virus.
Yes.
Because it's like fidelity.
Correct. Absolutely. So you can totally do that. This is perfectly general. I can think about, okay, so the genetic mutation of the virus is a little bit more complicated because there's more than, saying that I'm going to model it as a continuous variable between 0 and 1 is an assumption of I think a little bit too far. But certainly I can think about modeling the deviation from the genetic. So, I have some genome sequence to start off with, and I could see how many mutations occur to that original genetic sequence, and I could approximate it like that. Yeah. So you can certainly do that. That's a good question. And the first question was
that different persons might have different
styles. Oh yes, yeah. There's a lot of refining to do in the models. This was the first go at the problem. You could certainly change the assumptions. There are a number of things that happened after we published this the paper. One of which, in everybody, there's a lot of intuition that goes into the way you think you interact with people. And so people ask the questions that are intuitively clear to them. And then I'm like, oh, yes, that's a good question. Let me see if I can model that. Okay. So one question was, the one I originally started off with is how you would model disinformation, right? So in disinformation, you have purposeful injection of low fidelity information into a group, right? So that changes the mean, for example, in a specific way. The question is, how does that propagate? Another one is somebody said, well, is it true? Does your model account for the fact that bad news travels faster than good news? I'm like, no, but that's a really interesting question, right? So how would you try and model that? Well, good news, bad news. There's some emotional value attached to this. So you could weight the fidelity by an emotional value that you attach to it, right? So now you've got another parameter, or you can add it as another variable that's multiplied. So there's a bunch of things that we're currently thinking about that come from fun questions that people ask at talks. Christian.
Probably touching on the previous questions, and again, in the realm of speculation and drawing on an analogy to the pandemic, is it seemed to me as if your reference information, the broadcasting fidelity was a kind of constant throughout your system. Do you think there might be interesting sort of transitions if you had an unreliable broadcaster, sort of a super spreader of misinformation kind of thing?
Yeah, totally.
So there would be some.
There are lots of parameters you could tinker with. You know, you could make D3 a function of time, and then ask what happens to this if that's the case. You could ask what happens if you get let me speak in physics terms. If you get a quench broadcast versus some kind of slow broadcast, if you have a step function versus a parabolic tan kind of switching. There's lots of really interesting things to understand here. One of the things that I was quite keen on pursuing is, it comes from my other work in many body systems, so glass is a really interesting phenomenon, right? And that's because glass is not a solid and it's not really a liquid. It's kind of a liquid in slow motion. But the effect of that is that systems that have this kind of glassy transition, information spreads in a completely different way. Right? So if you're looking at stopping the spread of, let's say, disinformation, right, and you have a system that has a glass transition, then you could tweak the parameters to put it into a glossy phase, stop the spread of disinformation. I'm just having fun at this point.
Yes, just on your, I guess, hypothesis about bad news travels faster than good news. I suppose there would also have to be more opinion-based, like what you feel is good news versus what is bad news, and then you could have like an inverted system also. So, I mean, I'm just saying, like, there's so many different ways that you can model that, I guess. Yeah.
On the topic of the network structure, so Zira, with your question about where does the network topology actually feature in this? So it's firstly, it's not a continuous variable, right? It's topology, it's integers. So you have to actually kind of identify the topology, fix the topology, and then work within that. So WhatsApp has a particular architecture, right? That architecture is coded in the topology of the network of the graph. Facebook has a completely different architecture. Twitter has a completely different architecture. So, some of the other things that we're doing is changing these architectures and asking how information spreads, or misinformation spreads in Twitter versus how misinformation spreads in WhatsApp. And the difference between these and Facebook. And the difference between these things is basically the way that people interact with each other means that the network architecture is different, means that the topology of the graph is different.
Thank you very much, Jeff. Very interesting talk. I wanted to know two things. Admin only, the groups where only the admin may communicate. Is that what you mean by broad?
Yes.
Okay, so that was the one question. And then I wanted to know what parallels have you, what parallels do you anticipate one could see in communication networks that are used often in business and in software development, like Discord and Slack, and even better, where often very big decisions are being made there, and the information flow is really critical there.
So this falls into the category of looking at different networks.
But shouldn't those two are probably a little bit more like WhatsApp than Twitter and Facebook?
Possibly. I don't use Slack enough to and definitely don't use GitHub enough to understand what its architecture. Yes. But if there are parallels, then it's probably that a few things can be tweaked, but it should still be applicable, I think.
Yeah, thank you. And then I thought, just as a takeaway from me is keep my group smaller. Don't be on too many groups, and change the groups and
Then my job is done. Yes. Well, that's really the takeaway that comes out of this for me as well.
There's a question from an online participant. That please, you're allowed to speak. Unmute yourself and you can ask your question, please.
Thanks. If this is for me, Jeff, one thing that's worrying me about your conclusion, one key conclusion, is that discussion within a group in isolation will lead to a final result, which is the average, if you like, of what that group started out with. But that's not my experience, because it's saying we don't gain anything from discussion within a group. What I do gain is from the discussion within the group, I get a measure of the reliability or otherwise of the basis for the opinions of various people within the group. And I would hope out of that discussion comes not the original average, but a movement, unless you have some bias in the discussion, a movement towards the view which has a better objective basis. But how does that fit within your structure, or am I introducing a further complication? Thanks.
Thanks, Doug. I don't think you're introducing a complication. I think I'm averaging over longer time scales. So when I say it reaches a group average, I'm averaging over, sufficiently long time scales that your interaction within the group, with different people forming their opinions, your opinion of the different people that form opinions, all of that is averaged out over. If in addition, something changes, then that in this model is external stimulus. So that's you having external information and bringing that external information into the group. But in isolation, eventually the group will conform to something if you average out over a long enough time. So the internal dynamic
Mine wasn't very serious. So maybe there is also some application here in teaching and learning, because we've been often contemplating on this idea that maybe the classical approach of teaching, when you stand in front of the room and teach in one direction, is not the best. But it seems like your theory says that it is actually the best.
That's right. That's the takeaway. Broadcast signals are the best.
Okay, then on that note, now we know.
Followed by peer learning.
Thank you very much.
It's a pleasure. Thank you. Cool.
Maybe you have it already.
I don't, but thank you.
Thank you very much.
It's a pleasure.